All right, so we just looked at de Moivre's theorem for powers, right? Powers of complex numbers. But now we're going to look at roots of complex numbers. Now, roots are very interesting because you don't always get a single root. With a power, whole number power, you're always going to get just a single value out. But with a root, you're actually going to get potentially other things. So consider this, real numbers are complex numbers where the imaginary part is 0. So let me give you an example using some real numbers. For instance, if I wanted to do the square root of 9, we know that there are two roots, right? There's the principal root and the negative of that. So we actually have plus and minus 3, okay? Now I'm only showing you the principal root, but it's the square root of 9 really has two values, right? Because there are two numbers whose square is 9. What's interesting about that is if you plot those on a number line, out here is 9, over here is 3, and over here is negative 3. The roots are going to be equally spaced, in some sense, on that number line, right? They're equally spaced, symmetrical on either side of 0. Now let's consider if you wanted to find the number whose square is negative 25, for instance. Right, so negative 25 is also on the number line. But remember that if you take the square root of negative 25, the numbers you're looking for are going to be plus or minus the square root of negative 25, which is an imaginary number, right? Because there's a negative under the root. So this is really plus or minus 5i, okay? Well, 5i, plus minus 5i is on the imaginary axis, so it's no longer, well, that's not anywhere near vertical. The square roots of, the roots of negative 25 are then not going to be on the real number line. They're actually going to be on the imaginary number line, and they're going to be positioned at negative 5i and at positive 5i. Notice again that the two roots are an equal distance from 0, and they're also equally spaced around, around 0 in sense that they're, the angle between them, I suppose, is 180 in both directions. Right, so they're not on an angle from each other. They're on a straight line angle. Okay. Well, that's going to be very important. Both those features are going to be very important. In fact, there's a property of roots of complex numbers that I'm not going to get into the proof of this, but just to verify, that if you're looking for the nth root, we would say that there are nth roots. There are nth roots of any complex number. There are nth roots. What that means is if you're looking for square roots, there's going to be 2 of them. If you're looking for cube roots, there's going to be 3 of them. If you're looking for fifth roots, there's going to be 5 of them. If you're looking for 10th roots, there's going to be 10 of them. Okay? There are nth roots. There are 10 tenth roots, and there are 7 seventh roots. More specifically, they're all going to be on a circle of radius r, or the nth root of r. Okay, so if this thing here, a plus bi has an r value, right? It's using the Pythagorean theorem. Then these roots are all on the circle of radius nth root of r. Okay, so it shrinks it down, right? So if you were looking at the negative 25, you want the square roots of negative 25, you take the square root of the 25, which is 5, that's your new radius, okay? And so we saw that just a moment ago. If we're looking at square roots of negative 25, both of the square roots were on a circle of radius 5, right? You take the square root of that 25. All right, they're on that circle. Now they're equally spaced on that circle as well. So that's the other thing, is that the n roots are equally spaced on that circle. So if you were looking for fourth roots, for instance, you'd have 4 of them, and they'd be equally spaced on that circle. They'd be 90 degrees apart. Now they might be twisted a little bit. They may not be perfectly north, south, east, west. They may be on an angle, but they're still going to be 90 degrees apart from each other. So they'll be equally spaced around the circle. If we're looking for the 7th roots, then they'd be, the angle between them would be 1/7 of the circle. If you're looking for 6th roots, then the angle between them would all be 60 degrees, because that's 1/6 of a 360. Okay. So those are 2 very important features. The size of the circle that the roots are on is always the nth root of the radius of the original point, and then all the roots are equally spaced around that circle. Okay, so there's kind of some interesting stuff there. So let's take a look at how we actually calculate these things. If I want to calculate the nth root of a complex number, I'm going to go to the trig form. Obviously, you're looking at the nth root of, I guess it's this trig form, the nth root of r, whatever the radius is. And then for this, remember when we looked at powers, we multiplied the argument, we multiplied the angle by n. Well, here we have to divide. The problem is with division, there's more than one coterminal angle for the angle we're looking for. So we have to not only divide the angle given, the angle for this theta, but we have to add 360, divide that, add 360, divide that, add 360. So every coterminal angle must also be divided until we start repeating angles. And because we know how many there should be, we'll know how many angles we need. Okay, so let me demonstrate this. So as we go, this is going to be cosine. Now, I'm going to write a dummy variable, and then I'm going to throw alpha in there, okay, for the angle, and I'll explain then what alpha is going to be, where alpha equals theta over n. So, right, so you divide instead of multiply, but then you take theta plus 360, that gives you a coterminal angle, and divide that by n. And then you do another coterminal angle, theta plus 2 360s, right? You add another 360 and divide that by n. And you keep going until you get n of these terms. Well, that would be when you multiply by n minus 1, right? So that would be up to theta plus n minus 1 of 360 all over n. Now this is kind of clunky to look at. So your book actually defines alpha as theta plus a constant times 360 over n, where that constant is 0, 1, 2, up to n minus 1. All right, so if you're looking for 10th roots, you're going to have 0 through 9 here, right? 0 through 9 is 10 different values. That gives you the 10 different angles, and they'll be spread equally. They'll be spread equally around the circle. Okay. If you're looking for a 7th root, then you'd have 0, 1, 2, up to 6. Okay, and that will give you, 0 through 6 is 7 different angles. All right, so let me demonstrate how this works with an example. So let's say I want to find the third roots of, we'll do an easy one. We'll do the third roots of, well, now let's do something, let's do 1. The third roots of 1. It's kind of interesting. The third roots of 1. Now, on the real number line, that's like the cube root of 1, which is 1, right? So 1 is obviously one of the answers, but there's two other complex number answers, right? And they're going to be equally spaced around a circle of radius 1. So what I want to do, so this is 1 plus 0i, right? If you think about the rectangular form, the 0 is your imaginary part. So on our formula, I know that for the point 1, we know that r is equal to 1 because that's the distance to the origin, the origin is 0 there. And theta is 0 because the angle up from the real axis is 0. So the first root, so if let's see, the third root then of 1 is equal to the third root of my radius times the cosine of alpha plus I sine of alpha. So now I got to figure out what the alphas are. Well, alphas are theta over n, right? That's the first one. Well, theta over n is going to be 0, because that's 0 over 3, which is 0, right? I'm just using my angle here and my n value of 3. So the first one is just 0, so it's going to be the cube root of 1 cosine of 0 plus I sine of 0. Simple. Those calculations are pretty simple because we know the cube root of 1 is 1. We know the cosine of 0 is 1 as well. And the sine of 0 is 0. And so 1 times 1 plus 0 is 1. So the first root is just 1, which we already knew that, right? That's the real number value. So let's look at the other two. Now I'm going to erase some of this stuff up on top so I have some more space up here. So the other alphas, I did one of the alphas is theta over n. Remember the alphas are going to be theta plus k times 360 over n. I've done one of them, and remember k is equal to 0, 1, and 2 in this case because we're looking for cube root, so it always ends one less. That means there's 3 of them total, 0, 1, 2. If I kept going with the k values, 3, 4, 5, I'd just be repeating the first 3. Right? I'd be getting coterminal angles and just going around the circle more and more. So, I did the first one where k was 0. Now let's do k equal 1. So that would be alpha is 0 plus 360 over 3, which is, well, 120. 120 degree angle. Okay? A 120 degree angle is in the second quadrant, and it would be coming, let's see, 30 degrees off of the 90 degree angle, right? So this is 30 here, oops, and that means that this is 60 down coming off of the negative real axis, okay? So the point then that we'll be looking at, this is a 120 degree angle. The actual point that is a radius of 1, remember it's got to be the same radius, same distance. So the radius is 1, we already calculated that. So to find that angle, or to find the coordinates, the A and the B, I need to calculate cosine alpha and sine of alpha, which is cosine of 120 and sine of 120. Now I could do that on a calculator, but if I want the exact form, which is obviously nicer, and this is one of our nice triangles, or corresponds to one of our nice triangles, I can go ahead and do that. So I want 30, 60, 90 triangle, and then the x value here, how do I do that? So the cosine, well, let's do this. Cosine, so 60, 120, cosine is adjacent over hypotenuse, that's 1/2. So the cosine of 120 is equal to 1/2. Actually, it's negative because that corresponds to the negative the negative x direction there. So that'd be negative 1/2, and then the sine of the 120 is going to be the opposite over hypotenuse. That's √3 over 2, and that's positive because that's going up. The √3 is going up. Okay. So that tells me that the next value is going to be 1 times, because the root of r is 1, 1 times the cosine of 120 plus I sine of 120 is going to be equal to negative 1/2 plus √3 over 2I. Okay. So that's definitely going to be one of our cube roots. And then finally the last one, I need the k value to be 2. So I need to erase a little bit more here. Let's get rid of this, since we already have that. Okay, so the last one has a alpha value, or no, I'm sorry, a k value of 2. So alpha would be 0 plus 2 times 360 all over 3. Well, 2 times 360 is 720. 720 divided by 3 is 240. So that's a 240 degree angle. And that makes sense because that's another 120 degrees down here, right? So all 3 of these angles, this one here and this one here, they're all 120. That equally spaces those roots around the circle of radius 1. And so at a 240 degree angle, our values are basically going to be the same, except the signs are different. We're going to have both negative values on this one. So we have negative 1/2 minus √3 over 2I. Okay. So there's symmetry here between those 2 points. So we have now 3 points. All 3 of these roots are equally spaced around a circle of radius 1. And if I were to cube each of these numbers, this one here, this one, and this one, they'd all equal 1 when I cube them. I could even verify that for you just to show you. Obviously, this one here, if I cube it, it'll work. Maybe I'll try one of these just to verify it to you, that it will work. And I guess I'm erasing the one I was going to do, so I'll do the other one. Okay, so let's cube this one here with all the negatives. That'll be fun. So if you think about 1/2 minus, or negative 1/2 minus √3 over 2I, and I want to raise that to the 3rd power, I would be multiplying 3 of them. Now I could do this in the trig form. With the r's and thetas, but just for practice, let's go through the hard way. Negative 1/2 times negative 1/2 is positive 1/4. Then here we'd have a positive √3 over 4 times I. Then here I have a positive √3 over 4 times I again. And here I have a positive 3/4 I squared. Right? When I multiply those out, all of that is going to still be multiplied by my other one, which we'll do in a moment. But I've got to simplify in here first. Well, the I squared is really a negative 1, so that changes this sign. So it's 1/4 minus 3/4, which is negative 1/2. So I get a negative 1/2. And then these two, √3 over 4 plus √3 over 4 is 2 √3 over 4. And if you think about 2 √3 over 4, reduce those out, you get √3 over 2. So this is √3 over 2I. And then I still have to multiply by negative 1/2 minus √3 over 2I. and then we go through and distribute again. So here's a positive 1/4. Here is a positive root 3 over 4i. Here is a negative root 3 over 4i. That's nice. And here is a negative 3 over 4i squared. That look right? I think that all looks good. Then I simplify, and I get this term and this term drop off because one's plus, one's minus. And then I get a 1/4. And remember, I squared is really -1. The double negative makes that a plus, so that's plus 3/4. And at the end, 1/4 and 3/4 is 1. So when I cube it, I get 1. So it must be a cube root of 1. That's interesting. So it worked out. And if I repeated that process with the other value we found, it would work as well. Okay, so that's just to verify that there are more than one cube roots of 1. So if someone says, what's the cube root of 1? Don't just say 1, say 1 and -1/2 minus root 3 over 2i and -1/2 plus root 3 over 2i. Okay, so there are actually 3 cube roots of 1, and in a similar way you can find nth roots of any number, nth roots of any number. Okay.